Hi, I'm Michelle Kelsey. I'm Product Line Manager for Magnetic Sensing here at Freescale. I'm going to be talking to you today about an extrinsic solution board that we have available that showcases our MAG3110 3-axis accelerometer with a sensor fusion controller, as well as our MAG3110 3-axis magnetometer. The MAG3110 magnetometer is a 2x2 by 0.85 millimeter DFN 10-pin package. It has a dynamic range of 1000 microtesla. It also has a resolution down to 0.1 microtesla per bit. It has a supply voltage of 1.95 to 3.6 volts, as well as selectable output data rates up to 80 hertz. It has an I2C interface to connect to the processor, and it also has very low noise to support e-compass solutions. The MMA9550 accelerometer is a 3-axis accelerometer, 14 bits, as well as a 32-bit coal-fire processor. It allows for implementing the sensor fusion that we're going to demonstrate today, allowing for the accelerometer data as well as the magnetometer data to provide tilt compensation algorithms as well as magnetic calibration. Here is the graphical interface that we're going to be showing a lot of the capability on, and to simulate the environment of a mobile phone, I have a magnet here that I'll place on the board. There's quite a bit of magnetic interference in any PCB, especially in a smartphone situation where you have a speaker, you have a radio shield, any type of magnets for the open and close detection on the hinge, as well as the camera module. And all of those provide this magnetic interference that needs to be calibrated and compensated for. And with that, we're going to demonstrate this. So on the graphical interface, I will configure the default configuration, and then we will start the demo by pressing the start button. So you will start seeing some values show up, and what you're actually seeing is the output directly from the magnetometer here. You see the acceleration data directly from the accelerometer embedded in the 9550, and then the calibrated data of the magnetic sensor, and then we also demonstrate the roll, pitch, and compass. First off, I'm going to actually go and change this to microteslas from counts, so the data is more visibly apparent. Right now, what we're seeing directly from the magnetometer are these values here, about 500–600 microteslas, and you're seeing this due to some of the soft iron and hard iron distortions that are apparent on the PCB in the environment that we have. On the accelerometer, you're seeing 30 millig's or so on the X and 20 millig's on the Y with the balance of the table, and then you're seeing about in the 1G range for the Z-axis. For the magnetometer, you're seeing the calibrated values that's being done based on the solution that's provided here. The hard iron that we're detecting with the magnet you're seeing here. And what's done is in the background, the MMA950 will be sampling various outputs from the magnetometer as well as the accelerometer. So as you move the board, you see those values change, and it's creating it's doing the reading for the offset for the hard iron as well as the soft iron matrix that you see here. And so we'll turn it around just to get quite a few data points. And as you see that, then you'll start seeing more of a correction factor on the magnetic output.
Hello, I'm Talat Özyajlar. I'm the Systems and Applications Engineer for MAG3110. Here we have a 6 degrees of freedom PCB that uses MAG3110, which is the magnetometer, and MMA8451, which is an accelerometer. Freescale's algorithms use this information from the both sensors to get a reasonable, to calculate the vectors to aid us in various applications and demonstrations. So you can go to Okay, the main advantage of having a magnetometer as opposed to a gyroscope is the power consumption as well as the drift. So by using a magnetometer instead of a gyroscope, we're hoping to get around both of these problems because the vectors are fixed, the gravity vector is fixed, and the magnetic vector, Earth's magnetic vector is fixed. So we can look at the applications now. Here you can see we already calibrated our sensors and our application is running. We're able to see the raw data, magnetometer data, acceleration data, and we are actually have the mag flat, which shows the tilt compensated magnetic data, and then we're calculating the roll angle, pitch angle, and the heading, compass heading. And we have our inverse soft iron matrix displayed and the hard iron offset. And now I'm going to go to the e-compass screen here. Here we can see actually the heading. I'm going to point to north with this PCB. Now it's 0 degrees, and I'm going to bring it back to south, which is plus or minus 180 degrees here. So like so, we can point in different directions and find out our heading. We can see our pitch angle, and then we can also see our roll angle. And if you see, the heading will not be affected very much, minimally affected by the roll and pitch. Okay, so I'm going to go to the air mouse screen here. So now I will take control of the cursor by our the 60 degrees of freedom PCB. So now here you can see by moving the PCB, basically just intuitive pointing gestures, we are able to move the mouse cursor wherever we want on the screen. So now, as opposed to a gyro, here we have no drift, and by using the magnetometer, we're trying to replace the gyro functionality. Now in the next screen, I'm going to control Google Maps, and by using our PCB, we have mapped the tilt position to aid us in translating the map, the place where we're looking at on the map. So here you can see now our pointing direction in the upper left corner of the screen is changing as we rotate the PCB. So like so, there's a little delay due to the PC itself. Okay, so if you can see now we're facing north. So as we change the orientation of the magnetometer of the PCB, you rotate the map. So if we're going to go right or left, we basically just tilt this PCB, and the display will move as intended. Like so here. This concludes our demonstration. For more information, you can go to www.freescale.com/magnetics. Thank you.